In this research paper titled, Energy Considerations of Large Language Model Inference and Efficiency Optimizations, the authors, including Jared Fernandez, Clara Na, Vashist Tiwari, Yonatan Bisk, Sasha Lachoni, and Emma Struble from Carnegie Mellon University and Hugging Face, explore the growing energy demands of large language models, or LLMs, and how to make their inference processes more efficient. As LLMs continue to grow in size and popularity, their computational and environmental costs are rising sharply. Previous studies have mostly focused on reducing latency in controlled settings, but they've often ignored the real-world scenarios where these models are used, such as in conversational AI or code generation. This paper takes a deeper look at the energy implications of common efficiency optimizations across a variety of natural language processing and generative AI workloads. The authors introduce a new modeling approach that simulates real-world LLM workflows. They do this by binning, or categorizing, the distributions of input and output tokens, and by varying batch sizes to mimic how these models handle different tasks. Their analysis covers multiple factors, including software frameworks like PyTorch and vLLM, different decoding strategies, various GPU architectures, online and offline serving methods, and configurations for model parallelism. Through their experiments, they demonstrate that the effectiveness of these optimizations depends heavily on the specific workload, the software being used, and the hardware involved. For instance, simple estimates based on floating-point operations or theoretical GPU utilization don't accurately reflect actual energy consumption in practice. This means that without careful analysis, we could be underestimating the true energy costs. One key finding is illustrated in their figure, which compares energy use in kilowatt-hours for different setups. Using an optimized version of vLLM, they show that energy consumption can approach theoretical ideals, reducing total energy use by up to 73% compared to an unoptimized PyTorch baseline. This highlights how proper application of efficiency methods can lead to substantial savings. The paper points out that data centers are projected to consume between 9.1% and 11.7% of total U.S. energy demand by 2030, largely driven by AI workloads like LLMs. Companies like Meta report that inference alone accounts for up to 70% of their AI power consumption, while Google and AWS attribute even larger shares to machine learning inference. This underscores the urgency of addressing energy efficiency in deployment, not just training. In their introduction, the authors emphasize that while LLMs have improved performance, this has led to massive investments in hardware and energy infrastructure. Studies from 2025, such as those by Isaac, Smith, Kai and Sophia, and others, predict significant increases in energy demand, water use, and carbon emissions. To create effective energy policies, it's essential to understand the computational demands of both training and inference, with inference being particularly critical due to its repeated use. The research community has developed various optimizations for inference, including algorithmic improvements, better software frameworks, and advanced hardware accelerators. However, most of these have focused on speed metrics like latency and throughput, often tested in simplified environments. This paper fills a gap by examining energy costs in more realistic settings, covering tasks from basic NLP like sequence tagging and summarization to complex ones like synthetic data generation and chain-of-thought reasoning. Their empirical analysis reveals that factors like data dimensionality, decoding strategies, serving frameworks, compilation techniques, GPU hardware, model parallelism, and architectural variance all play a role in energy consumption. For example, they show that online serving, where requests come in real time, differs significantly from offline batch processing in terms of efficiency. Ultimately, the authors argue that by applying the right combinations of these optimizations, it's possible to achieve major reductions in energy use. This not only helps in making LLM deployment more sustainable but also informs the design of future AI infrastructure.